Welcome everyone, and today I'm going to talk about battery modeling. So that's something I've been looking into in the past few years since I joined SCM. And so I think it's of course an important topic because we all know that it's a very fast-growing field. So here I'm showing some prediction. So the battery market, so the lithium ion here, demand, so is expected to grow by about 30% in the next 5 years. And it's interesting because if you also look at the past prediction, they were underestimated basically. So we can expect this market to be even above this 30% growth. So battery, so they're here, right? So they're powering our mobile device, but mostly this market is being driven by the electrification of our transportation, as you can see in the bar. So they're here, they're working now. There still remain several challenges to overcome to make them better. So I'm showing just one example here about lithium. So we have quite a lot of lithium, and so the issue that could come in the next years, in the next few years, could be just production supply shortage. So there are like several challenges that have to be overcome. So we want battery to perform better, longer, to charge faster, and also at the same time to be more sustainable. So all of this requires effort in the reach and development, and there is no doubt here that modeling and simulation can help accelerate to bring those products to the market, but also of course lower the cost. So today I'm going to talk about atomistic modeling mostly. And what's nice about atomistic modeling is that even though it is what we simulate, it's about 10 order of magnitude to the actual real battery. So there are a lot of things that you can calculate from the atomistic point of view, and you can directly connect the prediction to the actual experimental properties. So I'm showing here a few of those properties. They cover most of the component of the batteries. And so what I'm going to do today, so I'm going to deep dive in a couple of those. So if you follow us previously, so I'm sure you've seen those. But what I'm going to stress today, I'm going to talk about the tool that we've developed in order to do some more accurate prediction and also faster predictions. So I'll talk about machine learning and how you can optimize, fine-tune those methods to get better prediction, basically. So just a very short overview. So I'm not going to talk very long, so about 20 to 30 minutes. So I'm going to start with just one slide overview of the Amsterdam Modeling Suite. Then, like I said, right, I'll show you some example. I'll tell you about the different machine learning potential that you can use with our software. And then I'll move on. So at the beginning, I'll show you things that work, and then I'll move on to showing you when things don't work. So what's the strategy to adopt, and how you can make those models better. And then at the end, I'll show you some results. So let me start with a quick introduction of the Amsterdam Modeling Suite. So we basically a software that covers mostly atomistic methods. So there are different compute engines that are all around this AMS driver. So the AMS driver, you can use it to perform various tasks. And then you can pick the different compute engine. They can be density functional theory, type binding, ReaxFF, and different interatomic potential. So there are about 3 ways of using the software. So either you use kind of the old way, which is writing input files and then submitting executing the code with command line, but nowadays, so you use in general the graphical user interface, so you can use the software to prepare the molecular system with the graphical user interface. You can set up the different type of calculation and also run the calculation and perform the analysis with the different graphical tools that we provide. And finally, the more modern approach, and also I would say the more thorough approach, if you want to perform complex calculation, is to use our Python interface. So with Python, you can also control everything. So all the way making the system, setting up the calculation, running, and doing the analysis. So let me start with just a few applications of atomistic simulation to predict battery properties. So here I'm showing lithium intercalation potential that have been calculated for a range of different type of materials. So the base material is the lithium cobalt oxide that I'm showing here on the top right. And so what I've done here, so it's a layered material, right? And so lithium can intercalate between the cobalt oxide layers. And so what I've done, so I've swapped cobalt with different transition metal, and also swapped the anion, which is the oxygen, with sulfur and also phosphate. And so this gives me a whole family of material. And I've calculated this lithium intercalation potential, which is just proportional to the energy difference between the fully lithiated material and the one without lithium. So there are two colors. One is calculated with density functional theory, and the blue one is with machine learning potential. So with DFT, you can do that, and it would take you maybe a week. But with the fast machine learning potential, it takes you just a few minutes. So just to show how you can use those models really to accelerate and screen many materials. Now you get this intercalation potential, which is an important property. But as a byproduct, you also get the volume change upon lithiation, which is also very important to predict the right packing of battery for EVs, for instance. Another thing you can do, so you can predict the entire loading curve upon when you apply basically a voltage, right? So this can be done with Grand Canonical Monte Carlo, where you're going to successively add lithium to the material and then find the lowest energy configuration doing Monte Carlo. And so this is shown in the bottom right with a reactive potential. So again, right, you find this free energy that corresponds to loading the material, but at the same time, you also find the volume expansion upon loading. So this is related to the energy density of the battery material. Now you might be interested into the dynamic of the ions in the material, and here I'm showing some example. So what you can do, you can run a classical or ab initio molecular dynamic simulation equilibrium, and you can track the position of the lithium ion in this case, which I'm looking into some solid electrolyte material. And by looking at this, the position of the ion upon the molecular dynamic simulation with respect to a reference, you can get what's called the mean square displacement. And from that, you can calculate the diffusion constant. What I'm showing on the left, so is the diffusion constant that's been calculated at different temperature. So it can help you extrapolate often to lower temperature, because we can only calculate a few picosecond or nanosecond. But you can also calculate the activation energy, right? Because the motion is thermally activated, so you can use an Arrhenius law to get this activation energy. So I'm comparing this with some experimental data. So this is for those fast ionic conductor. You can also calculate diffusion in the liquid, of course. And below what I'm showing, so if you want to have more information about the potential energy surface of the diffusion. So you can directly basically push an atom inside the crystal, and with techniques like nudge elastic band or PET scan, you can find the lowest energy path of the ion. So there are two sets of curves, because there is one curve with the material which is completely loaded with lithium, and the second curve is when there is a defect, a vacancy of lithium close by. So in that case, the trajectory of the migration is slightly different, and the lithium ion in this case, it's passing by a lower energy tetrahedral configuration. So there are two sets, a thin curve and a thick curve. So again, I've calculated the transition with density functional theory and also a machine learning potential. So all of that to stress that most of those properties that I've shown at the beginning can be calculated with DFT, but really, in general, it's missing sampling, and it takes a lot of time to get proper equilibrated molecular dynamics simulation. So recently, machine learning potential can really help make prediction more accurate. And so this is here, I'm showing a summary of the different machine learning models that you can use with the Amsterdam Modeling Suite. So we have an MLP modules. So from there, you can use some pre-parameterized machine learning model, and which include M3GNet, which is a graph neural network potential. So it's universal. It's been optimized to over the materials project database. So it pretty much knows all the atomic interaction that's in the periodic table. And we also have pre-parameterized model based on the ANI potential. So I think next week, Professor Isaev or someone from his team is going to discuss this type of model. So those are the pre-parameterized models. So you can just easily install them with our package manager, and then you can use them. You can accelerate them as well if you have a GPU. So that's one way of using machine learning potential. The other way, so if your favorite model is not there, so you can connect it to our ASE engine, and from there you can pretty much use anything that's been published. And all those models, you can use them with the AMS driver, right? So the AMS driver, you can do MD, you can do Grand Canonical Monte Carlo, you can do PET scan, NEB, and etc. Finally, so if those models, so they're not accurate enough for you, so we have this ParAMS tool that you can use to train and fine-tune the model, and that's really what I want to talk about it today. So that's what came this year with AMS 2024. And so again, right, so those machine learning models, they are in general pretty abstract black box. So it's great that they come with universal parameters, but in general, you want to double check what you're doing. And so here I'm showing some example where the model actually don't give you very accurate results. So for instance, some dynamical properties of water, some activation energy. So the one I'm showing, I've shown to you before, they were pretty reasonable with M3GNet. So you see that here for lithium, titanium, and sulfur, so it's about half the activation energy. For conformer, so if you're interested in conformer, this is the root mean square error compared to DFT, which is quite high, so more than 2 EV. And then you can use also those models to look at a chemical reaction. And here again, the activation energy for this water addition on propane here was wrong. So those are our tutorials that we have on our website, and so I'm going to show you how you can improve those models with our tool, and then you can go on our website and you can try it out, and you'll find all the details to do it. So again, right, those models, they're great, but you should always double check how they perform to the system that you would like to study. And so here I can just show an example related to batteries. So if you're interested in looking at the lithium diffusion in a mixture of the electrolytes, so this is ethylene carbonates, for instance, and PF6. So you might be interested in looking into the variation of the diffusion constant as a function of the concentration or the temperature, right? And so how you would proceed? So the first way of doing that, of fine-tuning or making a better model, would be to making a big data set and then just train a model. So we've developed this, we integrated training machine learning into our tool ParAMS. So with ParAMS, in the past, you could use it to train ReaxFF and XTB parameters, so DFTB parameters. And so we've extended it to train machine learning potential. And for now, you can train M3GNet and NeQuip. So the procedure would be to first start in making a data set. So some reference data that you've calculated with for example, DFT. And so this data would include some molecular dynamics simulation, volume scan to capture the different lattice parameters. So you can also do nudge elastic band or PET scan defect calculation. So you have to build all this data set. Then you can use ParAMS. So with ParAMS, you can import those calculations. Not that they don't have to be, those calculations don't have to be done with the Amsterdam Modeling Suite, but it's also compatible with external software. So you can use VASP, Gaussian, or Quantum Espresso calculation. You can import them. Then with ParAMS, so you're going to clearly see what type of calculation, the different frame that you have, if it's a molecular dynamics simulation, which engine it's been calculated with, which quantity it is. You can look at the value of the force very easily. You can look at the structure that corresponds that frame. Then you can split the data. So you can say, I want 20% in my validation set. And finally, you can define the model that you want to optimize. So all of this, either with the graphical user interface or with our Python interface. So you could say, okay, I want to train an M3GNet model, but I want to train it from scratch. That means that you can even redefine the architecture, the number of neurons, the different cutoff. Now, another way is to just take the universal model and fine-tune it. So fine-tune meaning that you're going to keep most of the first layer. You won't change those weight and bias, and you're only going to change the last layer. So in that way, the model already keep the knowledge of this chemistry that's been learned over the entire material project database. So it's really the recommended approach. Another thing that you can do, so you can say, oh, I'm not going to train just one model, but I would like to train a committee, so N model. So, and I'm just showing the example. So when you train it, you're going to see not one, but N curves. And what's nice with that is that, so the prediction is going to be the average value of those neural networks. But the standard deviation is going to give you an uncertainty of your calculation when you perform inference. So here I'm showing in a test case. So if you use our tool AMS to perform some molecular dynamics simulation, for example, you can display this uncertainty directly around the energy curve. So you're going to have this shaded region. So in this case, so the uncertainty is pretty much constant, but it could be some case where during the dynamic, you're going to reach a value or like a geometry with very high uncertainties. In that case, you would have to go back and maybe retrain your model. So that's often the case that you have to do when you use this procedure to train a model. You often end up with a test case that fails. So then you have to basically prepare more geometry, retrain the model, and iterate like that. So that's why we came up with a different approach, which is the active learning procedure. So in this case, you basically start from the result. You say, oh, I would like to perform in the end this molecular dynamic simulation, but I cannot do it with DFT. It takes too much time, or I have many of those, or I want to do it on a very large system. So you're going to define that molecular dynamic simulation that you wish to perform. And then you're going to run this active learning that's going to learn on the fly the parameters for the model. So what you need to do, you need to define what's the reference engine, right? So in general, you're going to use DFT. Then you define the molecular dynamic simulation. Now, sometimes just running equilibrium molecular dynamic simulation is not going to be enough for your system to sort of cross the transition state that you're looking for. So you can do non-equilibrium MD. So things that you can do typically is to deform the supercell of your system. So you're sort of going to teach the model various lattice parameters. So it's going to be more accurate, for example, to describe proper density in the end. But you can also use this deformation to sort of trigger chemical reaction if you want to make a reactive model. So that's what I call the reactor here, but it's really deforming the lattice parameter. We also have a tool that's called reaction boost, where you can provide an initial and a final state, and then it's going to perform a constrained molecular dynamic simulation to span the potential energy surface between those two trajectories. So it's really useful also to try to teach the model transition state. And finally, you can also perform Grand Canonical molecular dynamic simulation. And I'm showing cases where we train a model to describe a hydrogen on the ruthenium surface. So you define your MD. And then during the active learning, so the framework is going to split the trajectory into subsections. And at every checkpoint, so at first, the model is going to start running. So you need to have some initial training data to have an initial force field. It's going to use it to run the first section of the molecular dynamic simulation. At the checkpoint, it's going to perform a few reference calculations, calculate an error, and then if that error is not lower than some criteria that you've defined, it's going to add some of those reference calculations into the data set, retrain the model, and restart the molecular dynamic simulation from the last checkpoint. It's going to do that successively until it passes the checkpoint to address the second one. So basically what you'll get is the output I'm showing at the bottom right here. So I'm not sure if you can see my mouse, but so basically you can see here at step one, the first attempt, so it's going to be this first section, the first check was successful. So when it calculated a few DFT or a few reference calculation, the error was lower than that was defined at first. So then it continued along the second section of the molecular dynamic simulation. At the second checkpoint, he failed, so it was not accurate enough. Therefore, he added some data to the data set, went back to the first checkpoint, trained the model, and continued, and it's success for the second try. So in the end, you'll get a model that's going to be accurate enough along this entire trajectory. So that's one way of defining the active learning accuracy. The second way is like if you train committees. So in this case, you just define a maximum uncertainty, and whenever the uncertainty that's calculated, the standard deviation of the committee model. So whenever this uncertainty is going to go above your maximum uncertainty, then the model is just going to go back to the previous checkpoint, add data, retrain, and keep going. That's the second way of running it. Just showing you some results. So again, right, you can find that on the website. You can run those models yourself. So here, just really performing automatic training with active learning. So on water, so was able to fix the self-diffusion coefficient. So you see also from the RDF, so the structure of water is proper. You can also get a much lower RMSE for the different conformer, right? So it's calculated with respect to the lowest conformer here. And then the reaction energy and the transition state also have been properly defined. So I have some more examples that I've done myself, which are not documented. So here I was interested in looking at ionic diffusion in MOS2. So I've trained a copper diffusion, lithium diffusion in MOS2 with a vacancy, and also looked at the different MOS2 phases. So MOS2 can exist in 3 different phases, right? H, T, and T prime. And so if you take M3GNet, so he actually doesn't know any of those. So he only knows the H phase. So I'm showing, so in red, this is the potential energy surface that corresponds to the migration of the ion or the phase change calculated with M3GNet, with the universal potential. And then in blue is the reference calculation. So it's calculated with DFT. And in green is after the active learning workflow that's been applied. So here to make the ion migrate during the molecular dynamics simulation, I use the reaction boost that I mentioned before, right? So basically I have the initial and the final structure where the ion is at 2 different sites. And during the molecular dynamics simulation, I really pushed around the ion in order to cross the transition state and to really learn the potential energy surface, which is very successful at the end, as you can see. And even the different phases of MOS2 are known. Now, moving back or going back to the example of getting proper force field for liquid electrolyte for battery. So here what I've done, so I use this deformation during the active learning such that the model, so I define the checkpoints such that they going to check the accuracy when the system has different volumes. So I really try to span the different volumes. So I basically learn the proper density of the electrolyte here. And so you can see, so the diffusion at different temperature that I'm showing at the bottom right for lithium and PF6. So in red was the universal model. So it was several factors wrong. But then by just running this active learning automatically, I can get the proper diffusion. So sometimes, and actually in this case, I didn't run just one active learning, but I've coupled several of them in series. So you can do it at different temperature. You can do it with different concentration, which is what I've done here. And what's nice, so you can really make a Python workflow where, okay, I'm studying EC for now, but I can very easily switch to a different type of electrolyte, and my workflow is unchanged. So one thing that's good when you couple different active learning one after the other is that between them you can actually augment the data set, right? So one thing that I've done is that I'm also made a reactive potential. So using this reactor, I actually create new molecule. So during the active learning, so I break some bond. And so after the first active learning, you can just analyze the data, the structure. You can identify the new molecule. With our ChemTracer tool, you can actually identify all the chemical reactions that happen. And then you can map them. You can create a potential energy surface scan, and you can re-input it into the data set. And so you can sort of iteratively learn new chemical compounds. That's pretty much everything I wanted to talk about. So yeah, I just want to thank everyone at SCM here. So they've all contributed to make a better software. Now, related to machine learning, so I just want to thank Matti and Paul, who've been developing the model this year, and also Olivier and Lawrence that have been working on the graphical user interface. And with that, I would like to thank you all for your attention, and I can take any questions.